Hello and welcome to the Modern Embedded Systems Programming course. My name is Miro Samek, and in this lesson I'd like to go back to event-driven programming and active objects in particular. You've been using event-driven active objects since lesson 34, but perhaps it's not quite clear to you what advantages they provide in real-time programming. So this lesson ties together the concepts of event-driven programming, active objects, state machines, and real-time operating system, RTOS. I talked about all these concepts in this video course before. In fact, let's go back today to the project for lesson 27 about the RTOS. Copy the lesson 27 directory and rename it to lesson 43. Get inside the new lesson 43 directory and click on the project lesson to open it in the Microvision IDE. To remind you quickly what happened back in lesson 27, you experimented with a preemptive, priority-based RTOS kernel called QXK, which is part of the QPC framework. This RTOS kernel managed two traditional threads, Blinky1 and Blinky2. Thread Blinky3 was not started and not used, so let's just clean it up. To understand what the threads were doing, let's just build and load the code to the Tiva-C Launchpad board, and then watch how it works using a logic analyzer. The logic analyzer trace labeled Blinky1 corresponds to the Blinky1 thread, while the trace labeled idle corresponds to the idle thread of the QXK kernel. When you zoom in, you can see that both threads rapidly toggle the LED lines. Green LED in case of Blinky1 and red LED in case of the idle thread. Blinky1 runs for about 1200 microseconds, after which it delays its execution till the next clock tick. The result is that Blinky1 runs periodically every 2 milliseconds. The idle thread of the QXK kernel runs when no other threads are running. Now, there is also the Blinky2 thread, started with a lower priority than Blinky1. However, Blinky2 waits on a semaphore, which is signaled when the switch SW1 is pressed. So let's set the trigger in your logic analyzer on the falling edge of the SW1 trace, because the switch is active low. Now, when you start the trace, you don't see anything until the SW1 switch is pressed. By the way, I received quite a few inquiries about inexpensive logic analyzers. So today I'm using a very cheap logic analyzer that you can get for about $10 on Amazon.com and perhaps other online retailers. This logic analyzer works with the open source PulseView software that I'm using in this video. I've put some resources about the tool in the video description below. But going back to your real-time project, it has been specifically designed to showcase the principles of rate monotonic scheduling, RMS, also known as rate monotonic analysis, RMA, that I have introduced back in lesson 26. You can see here RMS in action. The Blinky1 thread with the highest rate runs at the highest priority, and because of this, it always meets its hard real-time deadline of 2 milliseconds, even if other threads are ready to run, like Blinky2 and the idle thread. Now, these were traditional blocking threads managed by a traditional preemptive priority-based RTOS kernel. The main question for today is, can active objects also do this? In other words, can active objects be compatible with the RMA-RMS method to deliver provably hard real-time behavior? Well, the purpose of this lesson is to find it out, as well as to explore other properties of active objects related to concurrency and real-time deadlines. The first step is to convert the Blinky1 and Blinky2 threads to active objects. You've seen such a conversion before, in the second half of lesson 34, so I'll go over this quickly. I will do the coding still manually today, although I will use the QM modeling tool for illustration. The QM model will be included in the project download for this lesson, so you will be able to try automatic code generation if you like. So starting with Blinky1, you need to create the Blinky1 Activeobject class that inherits the QActive base class from the QPC Activeobject framework. In C, you do this by declaring the Blinky1 struct with the first member super of type QActive. Blinky1 Activeobject will need a time event to replace the blocking time delay from the corresponding Blinky1 thread. The Blinky1 class needs a constructor function, as well as a very simple state machine consisting of the topmost initial pseudostate and just one state, active. The constructor must initialize the superclass QActive and also the time event to associate it with the Activeobject me and with the timeout signal. The topmost initial pseudostate arms the time event to fire in 2 clock ticks and then periodically every 2 clock ticks. With system clock ticks occurring every millisecond, this will make Blinky1 periodic with the period of 2 milliseconds. The topmost initial transition goes to the state active. The state active has only one internal transition triggered by timeout sig. So here is the skeleton code according to the optimal state machine implementation that I have introduced back in lesson 39. The action executed in the timeout internal transition is the exact body of the original Blinky1 thread, minus the blocking delay, of course. At this point you can delete the original code for the Blinky1 thread and move on to Blinky2. The Blinky2 Activeobject has quite similar structure to Blinky1, so I copy, paste, and replace Blinky1 with Blinky2 in the selected code. Blinky2 does not need the time event, and also it handles the button press event instead of timeout. The action executed in the button press internal transition is the exact body of the original Blinky2 thread, minus the blocking semaphore, of course. Now you can delete the Blinky2 thread code. But before deleting the Blinky2 thread instance and the Blinky2 private stack, let's think for a minute what you need for the Blinky2 Activeobject as the replacement. Well, you need the Blinky2 instance and you need an event queue buffer. The length of the queue must be adequate for the worst case scenario, but 10 events is typically a safe initial guess. On the other hand, and most interestingly, you no longer need the private stack for the Blinky2 Activeobject. This is because the underlying QXK RTOS kernel takes advantage of the non-blocking nature of active objects and executes them as so-called basic threads. Basic threads are run-to-completion activations as opposed to endless loops for traditional blocking threads that are then called extended threads. This allows all basic threads to use the same stack. In a minute you will see in the logic analyzer trace that these basic threads can still preempt each other. Of course, you also need to create the event queue buffer and the instance for the Blinky1 Activeobject, but again, you don't need the private stack for it. So the net result is that you save a lot of precious RAM, because stacks are typically much bigger than event queues. Moving on, you can delete the blocking semaphore, and instead of the extended Blinky1 thread, you need to call the constructor of your Blinky1 Activeobject. Now you need to tell the framework that you are starting an active object as opposed to an extended thread. For this you use the QActiveStart API. The signature of the parameters remains the same, so you leave the same priority. but you need to provide the event queue buffer and its length, and you don't provide the stack. You apply analogous changes to start the Blinky2 active object. So this would be all for main.c, but you still need to adjust a few things in the board support package, BSP. For example, you still need to define the newly introduced event signals like button press sig and timeout sig. For this, open bsp.h and declare an enumeration for the signals. Remember that in QP the signals cannot start with 0, but must be offset by QUserSig constant. Also, instead of the semaphore, you will be posting events to your active objects, and for that you'll need global pointers to them. You still need to add the definitions and initializations of the global active object pointers in main.c, and also you replace the signaling on the semaphore with posting an immutable button press event to the Blinky2 active object, just as you did it for the time bomb project in the previous lessons. This should finally be all, so let's try to build the code. Okay, the problem is the missing definition of the loop index that was dropped during copy and paste. Alright, the code builds cleanly, so let's load it to your Tiva-C Launchpad board and see how it works. Well, it works exactly as before, with the traditional threads. Specifically, pressing the button causes Blinky2 to run as before, but Blinky1 keeps running completely undisturbed and meets its hard real-time deadline every time. This is because Blinky1, having higher priority, freely preempts Blinky2. So even though Blinky2 does all its processing in run-to-completion steps, still it is preempted by Blinky1 multiple times. But this is entirely fine, because Blinky2 eventually completes its run-to-completion step before handling another button press event in the future. This illustrates the most important point of this lesson. The run-to-completion execution semantics of active objects and state machines does not mean that the state machine needs to monopolize the CPU for the whole duration of the run-to-completion step. Under a preemptive kernel, such as QXK, run-to-completion steps in active objects can and will be interleaved in time. This is handled entirely by the underlying real-time kernel. So if the kernel is preemptive, active objects can preempt each other and can meet hard real-time deadlines just as the traditional threads did. What that means that active objects with state machines, when combined with a preemptive priority-based real-time kernel, are as suitable for rate monotonic scheduling, RMS, as the traditional extended threads. Actually, active objects are even more suitable for hard real-time and for the RMS method in particular, because they don't share resources and instead use asynchronous events. But this is such a critically important aspect of active objects that it deserves its own lesson, and this is exactly what I will explain next time. If you like this channel, please give this video a like and subscribe to stay tuned. You can also visit statemachine.com/video course for the class notes and project file downloads. Finally, all the projects are also available on GitHub in the Quantum Leaps repository Modern Embedded Programming course. Thanks for watching.